Hey, hello, and welcome back to another exciting episode of Mr. Takeda Teaches Algebra. I'm your host, Mr. Takeda, and I'm going to teach you some algebra right now. This is lesson 9.1. We're starting a new chapter here on basically solving quadratic equations, but lesson 1 here is on the properties of radicals with the essential question, how can you add, multiply, and divide square roots and other roots, of course. So let's get started. Our core concept here, and this is what I'll be demonstrating in the next part here, is that the square root of a product equals the product of the square roots of the factors. Well, what's that mean? Well, let's say I had the square root of 45. That's this example. You actually break that down to the square root of 9 times 5. Okay, so I factor the 45 into 9 times 5. Why 9? Because 9 is a perfect square. And then I can think of that as really, this is this part here. This is the product of the square root. So the square root of 9 times the square root of 5, and the square root of 9, because it's a perfect square, is 3. So this is 3 times radical 5. So they're leaving out that first part over here, that this is really the square root of 45. We factor it down to square root of 9 times 5. Okay, so let's take a look at some examples. 108. The square root of 108 is, well, 108, we have to see if we can factor this. And if you're not sure, you can always fall back on this, right? 54, and that's 2 times 27, and that's 3 times 9, and this is 3 times 3. Okay, so I have a factor tree here. What I'm looking for is a pair of factors. I'm looking for the biggest perfect square I can get. So what I can do here is I can have a pair, a 2 and a 3 as a pair, and a 2 and a 3 as a pair. So I've got 6, 6, 3. So I can think of this as 36 times 3. 36 times 3. So 108 is 36 times 3. And the 36 is important because I have a pair of factors. That means it's going to have a square root of 6, right? 36 times 3, well, that's going to be equal to the square root of 36 times the square root of 3, which is equal to 6 times radical 3. And that's the simplified form right there. B, because this one, we've got x cubed in it, the biggest square root is always going to be 1 less than the odd exponent. So if it's an even exponent, it's a perfect square already. So x to the 4th, x to the 6th, x to the 8th, already a perfect square. If it's an odd exponent, the biggest perfect square will be 1 less, the exponent reduced by 1. So x cubed, I can think of as x squared times x. X squared is the biggest perfect square. Now I've got 2 perfect squares here now, 9 and x. So I can think of this as the square root. I'm going to list it all out here. The square root of 9 times the square root of x squared times the square root of x. Square root of 9 is 3. The square root of x squared is x. And then this poor little guy has to stay living in that little house, whatever you want to call it. He doesn't have anything that he can use to get out of the house. He's not a perfect square, so he's stuck in the house. That's kind of a fun way to say it, but don't really think of it that way. It's I can't simplify him any more than the square root of x. Okay. Quotient property of square roots works exactly the same because, again, multiplication and division are really the same thing. But this idea here, the square root of 3/4, I can think of as the square root of 3 over the square root of 4. And now I can simplify the denominator to the 2. All right? Same idea. We can split them is the idea. Square root of 15 over the square root of 64. So I can split these. And then the square root of 64 is 8. Square root of 15 times square root of 8. 15, I can only factor to 5 and 3. There's no perfect square there. 64 is already a perfect square, so that becomes square root of 15 over 8. B, square root of 81 over x squared. Well, that's going to be fairly simple, I think. You can kind of see this one. The square root of 81 over the square root of x squared. The square root of 81 is 9. The square root of x squared is x. So pretty simple. Again, we can just kind of split the denominator and the numerator and work on them separately. Okay. Properties of cubed roots. Now, cubed roots is going to be a little bit different. Let me do the first one here first. Trying to find the cube root. I can think of this as negative 1 times 128, and then 2 times 64, and that's 2 times 32, and that's 16 times 2, and that's 2 times 8. You get the idea. 2 times 4, and 2 times 2. Okay, so what do I have here? I've got 1, 2. I'm going to keep track. 1, 2, 3, 4, 5, 6, 7. I've got 2 to the 7th power and negative 1. So I can think of this as the cubed root of negative 1 times 2 to the 7th. So I can think of this as the cube root of negative 1 times the cube root of 2 to the 7th. Okay, so the cube root of negative 1 is going to be negative 1, because negative 1 times negative 1 is positive 1, times negative 1, again, gets me negative 1. So this is just negative 1. Now, let's talk about the cubed root of 2 to the 7th power. Every third power is going to, not third power, every 3, 6, 9 are going to be perfect cubes, right? To the third power, to the 6th power. So I can think of this as the cube root of 2 to the 6th. I'm going to split it here before we kind of save myself a step. Cube root of 2. Okay, so the cubed root of 2 to the 6, 6 divided by 3 is 2. So this is 2 squared, this is 4. So this is negative 1 times 4 times the cube root of 2. So this comes out to be, I'm going to put it over here, negative 4 times the cube root of 2. Okay, I'm going to erase this, give myself some room to work here. I'll probably leave the last one off. We can do that later. The cube root of 125 x to the 7th. I can think of 125 is already a perfect cube because it's 5 cubed. So the cubed root of 1, I'm going to draw a line here so we can. Cube root of 125 times the cube root of x to the 6th times the cube root of x. Okay, so the cube root of 125 is 5. The cube root of x to the 6th, 6 divided by 3 is 2. So x squared times the cube root of x. Okay, so let's do C. This is the cube root of y over the cube root of 216. The cube root of 216 is just 6. So this is just cube root of y over 6. 6 times 6 is 36 times 6 is 216. So again, you could have done that with a factor tree if you're not sure how to get the cube root of something, like I demonstrated. Rationalizing the denominator. Now, this is a very important idea. Very important. There's a rule in math that says that when we simplify an expression, we cannot leave a radical in the denominator. So we have to, it's called rationalizing it. We need to turn it into, we need to make it rational, which means it's like a ratio. How do we do that? Well, we do that like we do any other fraction that we want to use, that we want to turn into a um, equivalent fraction. So what I'm going to do here is I'm going to multiply this by radical 3n over radical 3n, right? So this is again that kind of, this is a 1, has a value of 1, but I'm multiplying the radical by itself, which kind of undoes the radical. So square root of 3n times the square root of 3n is just 3n. Now I can multiply these together and get the radical 15n. Right? Let's take a look at the cubed root 1 here at the bottom. We want to multiply this again. This is going to be multiplied by the cube root. Well, let's kind of simplify this down first here. Here's cube root of 9. Well, we know 9 is the thing about this one. We know 9 is a perfect square. It's 3 times 3. So what we want to do here then, let me put it over here. Sorry for the delay in explanation. Okay, we know that 9 is a perfect square because it's the cube root of 9 and the cube root of 9. 9 is a perfect square. So 9 is 3 times 3. So what I can do then is multiply this by another cube root of 3. Right? I have to do the same top and bottom, just like any other equivalent fraction work that we've done. So the cube root of 9 times the cube root of 3, we're not undoing this. What are we doing? We're turning this into the cube root of 27, because 27 is a perfect cube. Up here I'll have 2 times the cube root of 3. And then what is the cube root of 27? 3. It's 3. 3 times 3 is 9 times 3 is 27. So this becomes 3. So 2 times the cube root of 3 all over 3. Now, we have this other idea called conjugates. Conjugates are these are conjugates. These are examples of a radical b plus c radical d and a radical b minus c radical d. And we can use these because of the, remember we have the special products thing where we're adding and subtracting the same two terms. That gets us like the difference of squares thing, right? Okay, so let's take a look at an example. I want to rationalize this using conjugates. So 7 over 2 radical 3. I'm going to multiply this by 2 plus radical 3, top and bottom. Okay. So what does that get us? Well, I know that our difference of squares pattern, 2 radical 3, I'm sorry, 2 minus radical 3, 2 plus radical 3, they have the sum of the difference. I take the first term, I square it, 4. It's going to be the minus because it's going to be a difference of squares. And then radical 3 squared is 3. Right? So that's these two things multiplied together. And this one is just going to be kind of distributive property. So 7 times 2 is 14. Plus 7 times radical 3 is 7 radical 3. And then I can simplify the bottom into a 1. Which is just 14 plus 7 radical 3. All right. So this is again that special products, that multiplying special case here. Okay, so we have some examples here for adding and subtracting radicals, and this is just the same as collecting like terms, but instead of a variable like 5x and y and 8x, we have common radicals, not like, or they're like radicals. Okay, so I can combine 5 radical 7 and negative 8 radical 7 into negative 3 radical 7. So I simplify this, this is radical 11 minus 3 radical 7. Okay, it's just like collecting like terms. When you have a problem like this one, 10 radical 5 plus radical 20, we have to change the radical 20. We have to simplify it first to see if we can match this. So radical 20, I'm going to do the work over here. Radical 20, I think of as, this goes back to what we did earlier in the lesson, 4 times 5, because radical 4 is just what? 2. This is 2 radical 5. This is 2 radical 5. So I can think of this as 2 radical 5. So now I have like terms. So 10 plus 2 is 12. This is 12 radical 5. This one's pretty straightforward. I have the cube 6 times the cube root of x plus 2 times the cube root of x. So this is just, of course, 8 times the cube root of x, distributive property. Distributive property here. I know this lesson is going a little long, but there's lots of good examples here. Radical 5 times radical 3 is radical 15 minus radical 5 times radical 75. 5 times 75 is 375. Okay, and now we have to simplify these to see if we can have like terms here. So 15 I can't simplify, but 375 I can think of as 15 times 25. And then the square root of 25, of course, is just 5. So radical 15 minus 5 radical 15, negative 4 radical 15. I think that's it. That's it. Okay, I know that was a lot, but we need to lay some groundwork here for a lot of stuff we're going to be doing in the rest of the chapter. So there's lots to do. We didn't even do the word problems. So thanks for hanging in there. Make sure your notes are complete and good, and may the force be with you. Bye-bye.